packed presentation today, so I'm going to get started. So welcome everyone to our first Ask a Mathematician panel discussion, and we're very glad you could join us today. My name is Dr. Pamela Britton, or Dr. Pam for short, and just a little bit about me. I have an undergraduate degree in chemistry, math, and physics. I have a master's in mathematics, a PhD in math education, and I'm a certified teacher from grades 4 to 12 in math in Ontario. So based on all of that, you would probably think that I am super good at math, and I always have been. But the truth is, I've actually always struggled a bit in math in school, but I've always loved the subject. So I kept working at it, and luckily, I have now found myself here at the Fields Institute for Research in Mathematical Sciences, where mathematicians from around the world come together and they collaborate on math. They talk about it, they have workshops and seminars about it, they write mathematics on the chalkboards on the walls, and best of all, they enjoy lots of cakes and cookies and coffee, because apparently mathematics runs on sugar and caffeine, or so I've been told. So my job is actually meeting these wonderful mathematicians and learning about what they do, and then bringing it into classrooms like yours, where I get to show you all of the amazing mathematics out there, and how the math that you actually study in school now forms the foundations for some really cool and interesting mathematics, some of which you'll actually learn about today. So first, some housekeeping. This event is being recorded. So for student privacy, your cameras and microphones have been turned off. However, the chat and the Q&A, which is found under the More button at the bottom of your screen, it's 3 little dots, are wide open. And for questions, and our moderator extraordinaire, Jordana, who is our manager of communications here at Fields, is going to be watching the chat and passing on questions to me and the panelists. So please feel free throughout the presentation to communicate with us, and make sure that your class has a dedicated typer ready to go. Also, this session is scheduled to end at 2:30. But our panelists are happy to stay longer if there are additional questions. If you can't stay, that's perfectly fine. It's being recorded, and we'll put together some bonus content for you to view from that. Okay, so without further ado, let me introduce you to today's wonderful panel of math experts. I am joined today by Dr. Sophie Spierkel and Karen Yates, both from the University of Waterloo. Jeremy Chu, who is an operations research PhD student from Simon Fraser University. Dr. Daniel Johnstone, who's joining us from Purdue University, all the way down in the US. And with me here in Toronto is Dr. Zach Walsky. So welcome to all of you. So why don't we start with a brief introduction of each speaker? So tell us who you are, where you're from, how did you get there, what it's like to be a mathematician, what do you do with your days, what do you like most or least about being a mathematician? Basically, tell us about your life and your mathematical journey. So why don't we start with Sophie?
My name is Sophie. I use she, they pronouns, and I will try to remember all the questions I'm supposed to answer right now. I'm originally from Germany. I'm now in Waterloo, Canada, and I moved here about 5 years ago. I work on a kind of math called graph theory, which I will tell you about very soon. My typical day consists of research and teaching, and I think my favorite part about being a mathematician is that I get to work on things that are fun and also get to work with other people pretty much all the time. So on a typical day, like this morning, I will sit in my office with a few other people and we will just think about fun questions. That's my favorite part. My least favorite part is when we're all stuck on those questions and don't get anywhere. But it feels a little better if at least there's a room full of other people who are just as stuck as you are. Those are the questions I remember.
Hi, I'm Karen. My pronouns are they, them. I'm a professor also in the combinatorics and optimization department here at University of Waterloo. I study combinatorial problems that come up in various parts of fundamental physics, especially quantum field theory, but also a bit on quantum gravity, which I'll be telling you about later. I grew up in Halifax, and yeah, I guess I've been a few places since then, including out at Simon Fraser University for a while. I was in Boston for a while. I have to say what I like the most about math and what I've always liked about math, even since I was a little kid, is sort of the solving puzzles aspect of it. And so sometimes I say that I have the best job in the world because I get to solve puzzles all day, and that's super great. And also, you solve these puzzles mostly with other people. So I'm going to echo what Sophie said there, which is also definitely part of the joy of it. I mean, I think the worst part is actually that, like any job, there's always some bureaucracy and stupid stuff like that, and I think that's the worst part. uh, yeah, and I say you can tell it's a problem, the style of problem that I'm gonna like if working on it involves scribbling little things on a piece of paper. So, my notes, they're often full of little things scribbled on a piece of paper, and that's how you know that it's the kind of math that I'm going to enjoy.
Hello, my name is Jeremy. I'm an instructor at Langara College, and I love math so much that I decided to go back and do my degree for the school to do some more mathematics. I said I love dogs, so this is my dog. This is Benji. Um, Aside from teaching, which is great, I enjoy teaching and I like talking about math. I now do operations research in healthcare. So I'm now applying math to try and solve problems that hopefully can help clinicians and doctors and different patients across Canada. I think my job involves two parts, doing math and then applying it. So I need to get better at math. That's still going to classwork, learning more calculus, learning more algebra, learning more graph theory. And then there's the aspect of applying it, which is really listening to what other problems people have, healthcare problems that are not inherently mathematical. But then I need to think about what I've learned in my math classes and how it can apply to help people in the healthcare. It's a lot of statistics and machine learning, but I'll use any tools at our disposal. I actually have come to love the bureaucracy. I shouldn't say that. I don't love the bureaucracy, but I understand why it's there. And I'm learning to do math that fits within the bureaucracy, which is a lot and a lot and a lot of listening. I'll tell you more about what got me into math, which is called mathematical modeling, when I get to my talk.
Hi, I'm Daniel Johnstone. I use he, him pronouns, and I'm a professor of practice at Purdue University. So I still do research. I still love research. It's where I started, but my job's focused primarily on teaching. This wasn't originally the plan. I did my PhD. I did a couple of what are called postdocs, sort of a little job after a PhD that's not quite a professor yet, where I did some research for a few years, but I eventually pivoted into teaching, and I do love mathematics. I do love doing research, but I guess what I love most about my own job is the teaching. I'm lucky enough at Purdue that I have a lot of my courses are introductory. I either teach introductory calculus to a big room of first or maybe second year students, or I'm given some introductory math courses for people who are just starting their math majors, the first couple courses of people who, if they really want to go into higher mathematics, I'm sort of giving them, teaching them their first sort of proofs, the basics of how to go just from calculus into sort of, beyond into what a math major will see. And I really, really love doing that. Didn't think about my least favorite thing. I mean, every day has lows. Sometimes when I'm working on a research problem and it's not going great, that can feel sort of icky, but it can feel great when it's going well also. But definitely, I love teaching mathematics. It's hard because teaching math is hard and learning math is hard, but definitely when I see somebody's eyes light up and they really sort of get something that they were struggling with before, which luckily happens a fair bit, that's definitely my favorite part of my day when that can happen.
Hi, I'm Zach Wolski, and I'm a mathematician and math educator in Toronto. What do I like? What do I not like? So I work in my math research is in number theory. As Daniel mentioned, I did a or he didn't mention my postdoc, but a postdoc is like a little job that you do after your PhD that is sort of introducing you to the research world. And I did mine in math education, where I worked at the university teaching and trying to understand how can we teach math better. So now I approximately split my time. The split is not like every day I do half math problems and half reading about teaching or teaching people things. It's more like this week I will focus on one thing, next week I will focus on a different thing. Um, and I guess I don't know. I don't have the same issues about bureaucracy that people don't like. I don't think that there's anything that I don't like about doing mathematics. It's so nice. So I hope you would all consider doing it too in the future and that it's helpful for you.
Perfect. Oh, I like that. All right. So the format for today is each one of our speakers will have a chance to tell you about something in math they find fascinating. And then we'll ask all of our speakers or targeted speakers some questions between the presentations. You'll also have a chance to ask questions in the Q&A in the chat as we go along as well. So let's start with Sophie, who is going to talk about catching ghosts.
This is a very important practical problem that I think all of us face on a daily basis. So I want to talk to you about how to solve this using math. And also, since Jeremy just bribed you with a dog, I'm going to level with him. This is my cat Brandy. And if you have a cat, or if you've ever met a cat, I think we all know one thing that is clear, which is that cats can see ghosts. And, right, a lot of the time when a cat is hanging out with you, they just stare off into space. And in fact, no, they are looking for ghosts. And so one important question is, well, what do we need to make sure that the cats can actually catch the ghosts instead of just kind of watching the ghosts and doing nothing? So let's say what this looks like. So this is a game where we have my cat Brandy and a ghost, and we have a bunch of rooms. And the rules are that Brandy picks somewhere to start out, and then the ghost picks somewhere else to start out. And on each move, Brandy can move to an adjacent room or stay where she is, so maybe she'll head here to get a bit closer to the ghost. And then maybe the ghosts will flee to room 4 to be further from Brandy. It's important here to note that, contrary to popular belief, ghosts cannot move through walls. They can only move through rooms that are actually adjacent. So in this example, you can maybe see that Brandy is going to have a hard time catching the ghost because they can just keep running clockwise and never actually catching up. So how many cats would we need to own in order to solve our ghost problem once and for all by making the cats catch the ghosts? This doesn't really sound like a math problem. It maybe sounds more like nonsense. But actually, there's a math theorem that says if you have a house which has only one floor, meaning that there aren't any stairs or elevators, nothing like that, then the number of cats that's optimal for ghost hunting purposes is 3, which is not at all obvious and is very deeply related to structural graph theory and what kind of graph you get if you live in a house with exactly one floor. And my favorite part in math is thinking about stuff. And when you see this question, I think maybe this convinced you that one cat can't always catch one ghost. But why is 2 not enough? Right? I told you 3 cats always works. Why not 2? And so, as your important homework, here is the construction of a house where you will need 3 cats. The black regions are rooms, obviously. All the rooms are triangles except the outer one, which is kind of a long hallway. And then there are doors everywhere that you could possibly put a door. So for houses with one floor, 3 cats is really the optimum. And then, now that I've told you this, we can think, what about other houses? What's special about having one floor? How many cats for 2 floors? What kind of layouts of your house might require more than 3 cats? Maybe 3 cats are enough for any house. And if I show you a house, how do you know how many cats you need? And which kinds of layouts are enough for 1 cat to be able to catch a ghost? Obviously, we always want to own more cats, but in order to have 1 cat be the sole ghost hunter of the house, what does your house need to look like? Turns out these are all questions that you can answer with math. And a problem we cannot solve is, what if the cat is on the side of the ghosts? That is not a math question. That's all I got for you. Um, study math so you can learn more about cats.
Awesome. Thank you. I like that look. And I wonder if that's why my dogs stare at walls, or maybe they're just bored, so that's what they're doing. So our first question is actually going to go to Karen, Daniel, and Sophie. So at what age did you realize that you wanted to be a mathematician? What made you realize you wanted to be a mathematician? And was it because you were good at math? So we will start with, we'll start with Karen.
All right. Okay, I guess I'm going to start with the later part of the question because at first I actually thought math in school was really boring. And so I'd said earlier that what I really liked was puzzles. And I distinctly remember being in grade 3, and in the classroom, there was one of these like boards with little puzzles on cards. And if you finished your math, which was boring, then you could go get a puzzle and do the puzzle. But of course, it's actually all math. And so I started to get into math, sort of math as math, when I was in junior high and high school, and I started writing contests, because contests are just puzzles done quickly. And I think it's important to note that you don't have to enjoy the quickly part of it, and research mathematics doesn't have that aspect, but it's all still puzzles, and it worked for me. And it was only really in university then that I really thought the math classes were like, wow, this is the place for me. And I remember sitting in my first year classes. I was actually an undergrad here at Waterloo, and then I went away and came back eventually. I remember sitting in those first year classes and thinking, these are my people. Because the classes now started to turn into puzzles too. You're thinking about how to prove something. You're thinking about what is the structure of some sort of object. And those are also puzzles. And also the beauty of mathematics starts to become, at least for me, started to become more clear at the university level. So I guess the age I really decided to become a mathematician was really at the beginning of my undergrad. Though certainly I'd enjoyed, especially the contest work and other kinds of puzzles, for a very long time.
Excellent. And how about you, Daniel?
Yeah, so I would say that I wanted to study math as soon as I sort of understood that studying math was something that you could do, but that didn't happen till very, very late in high school, sort of maybe arguably in university. Like I remember very early on, I had this incorrect conception of mathematics, that it was sort of very formulaic, very dry, very memorization based, and I didn't simply dislike that. I hated it. I pushed back against it because I didn't perform well, because I didn't like it. And teachers, please don't do this, but some of my teachers did. I was told that I was bad at it, and that couldn't have helped. But like as soon as I figured out sort of, wait a second, there is something here, there is some real depth to this. As soon as I sort of understood, and it happened a little later when I was sort of given some mathematics that, or at least was told that mathematics didn't have to be memorization based. It was about patterns, it was about games, it was about ideas, and indeed more like puzzles, to sort of echo what Karen said. And then I started to really love it, and as soon, sort of late in high school, when I was thinking about where to go to university, when I found out that, going to just study math was a possibility, I jumped headlong in. And of course, this solidified at the university level. I also loved my first year courses at the University of Waterloo. And they sort of, once I got there and once I started taking them, then I was hooked permanently. So that's sort of what my journey looked like.
Excellent. And how about you, Sophie?
I feel like our answers are sort of a coordinated mission to come to Waterloo and study math here as an undergrad, because that is the magical place where things change. And obviously my experience was completely different, where it's also true that math at undergrad was very different from everything I had done before, and it was much more fun. But it was not at Waterloo. Turns out other places can also do math, although I don't know if I'm allowed to say this since I work here. Come to Waterloo. But yeah, I think I never really had a point in my life where I really figured out this is what I want to do. I need to be a mathematician. I just kind of learned more about it and kept enjoying it. So I stuck with it, and here I am. And now I talk to people about cats for a living.
Sounds like a good way to do it. And as a member of the Fields Institute, I can say that there are many places that you can study mathematics. I'm not tied to one institute, to one university. So that's awesome. Next, we're going to have Karen, who's going to talk a little bit about the mathematics of time and space.
All right, thank you. So maybe this is going to have a somewhat different character. Despite what we just said, this is maybe a little less on the puzzle story, but a little closer, like fairly directly related to something I'm thinking about at research level right now. So I want to talk about space-time. And to keep it simple in this little story here, we're going to imagine that for us, we live on a line. So here's this line, and maybe you live right here on this line, or me, maybe. And maybe my friend lives over here on this line. And the other thing we have in space-time is we have time. So I want to think about time as moving forward in this direction. So there's time, it's moving up that way. And so if I'm just sitting here, and nothing interesting is happening, and I'm just moving forward, then I'm just sort of here, and I'm tracing out this path here in space-time. And maybe my friend will be a different color, is moving up here in space-time. Now, if I wanted to go visit my friend, what happens? Well, then I get to move in space and in time, right? So I move over towards my friend as time is passing, and then maybe I have a visit with my friend, and then maybe I go back to where I started. So, and notice that when I'm going to visit my friend, this line here, you'd say that line is kind of steep. So why is this line kind of steep? Well, you don't walk that quickly, right? So a lot of time passes, even though not that much space passed as I was walking over to my friend. So that's an important thing to keep in mind. This is steep because in there, I'm going kind of slowly. And well, what am I going slowly compared to? I'm going slowly compared to light, because light, of course, goes really fast. So if I send some light to see my friend, that light is going to get there an awful lot faster than I would have. So here, let's make some light, and here's some light, and I'm sending some light off to see my friend. No, that's not the color of the light. The light is going to be yellow. Here's some light going off to see my friend. There's some light going off in the other direction. All right, that's a little hard to see, so I'm going to put a line behind it. Here's the light. All right. And so you've probably heard that nothing, not even information, can go faster than the speed of light. So the point of that is everything in here, or a point of that is everything in here. These are all the things that I could potentially influence in the future. They're inside what's this light cone, as it's called. Because if there's something in there, I could at least send light there, and it would get there to that space in time. Like, so if it's over at my friend, the soonest the light could get to my friend is here. If it's somewhere further away, or maybe the soonest it could get to this far away would be over here. And it's okay if things go slower too, like me. I was slower than light, surprise, surprise. So I got to visit my friend here instead. So the point is, the stuff that's inside the light cone is the stuff that I could at least potentially influence. So maybe I'll write that down. Okay. And so we call that our causal future. So that's my causal future. And now, so for instance, I'm going to draw this thing again. So here's time, and here's space, and here's our light cone. And well, and in fact, and if you know a little bit of relativity, you probably prefer if I don't write the time and space axes, because really the part that matters is the light cone. So here's me, I'm here, and here's a point, and it's in my causal future. All right, and we're going to draw a line between points that are in the causal future of other points. I'll change color again. So here's a point, here's another point, and here's a line between them. But now this other point also has a causal future, because you can think about how fast light can go away from that point. And so there could be another point up here that's in the future of this point. Well, likewise, I could have some other point here in my future, and it has some light cone of the things that could be in its causal future. And notice that other light cone, it includes this point up here, so we'll draw a line between them. But these 2 points, they can't influence each other, because neither one is in the causal future of each other. And so this builds a structure and it's called a partially ordered set, or poset. And so one of the ways we can try to approach quantum gravity, which is one of the biggest dreams in physics today, is to discretize space-time and keep just the causal structure. And we do this by building a poset that has a certain discreteness condition that's called local finiteness, which I don't want to tell you what it is because it doesn't matter. And this is an approach called causal set theory. And then what do you want to do? Well, you want to look for discrete analogs of things that exist in space and time. And so and then you try to use tools from combinatorics and discrete math to try to understand what could be going on in the physics, as a model of space-time. And so just as one example, the volume in a space-time region becomes the number of points. And then there's lots of math that mathematicians who didn't think one bit about physics and they were just doing math because it was beautiful. There's lots of math that those people developed about posets. And so now we can use that, and we can say, okay, but I mean, I think posets are pretty cool just in and of themselves, but now I also want to try to use them to understand the physics better. And so I can bring to bear a lot of interesting pure math and try to have it tell me something about quantum gravity.
Very cool. Thank you. We got to see a little bit into the future there. The next question is one we often get asked by students, is what can you do with a math degree? Or why should I consider getting a math degree? So Jeremy, I'm going to get you to speak a bit about what can you do with a math degree and why non-mathematicians should consider also studying math.
So I'm a scientist and I believe in evidence. So I collected some evidence on my alma mater. Alma mater are my colleagues that graduated with me. And I just took notes of some of the jobs that they have holding a math degree. So there are also like the artists. Some quit their career and became a photographer, and that's totally fine. But I'm just focusing on the technical aspects. I think, in my opinion, one of the reasons that math is helpful is you're kind of good at, like, you're kind of not bad at everything. You're not necessarily good at anything. You're good at math, whatever that means, okay? but you're okay at statistics, you're okay at computer science, you're okay at physics. So it's extremely flexible. So for instance, my friends are now statisticians, actuary, business analysts, marketing consultants, software engineers, computer scientists, data scientists, healthcare research, and I'll come back to teacher in a moment, all right? So this is I'd say it's an advantage. Math keeps you very flexible. The slight disadvantage is that most of my friends needed to do a bit more school before they can get their jobs. So I'd say that's a slight disadvantage. But the advantage there is if you're not entirely sure what you want to do, math is the common language to a lot of different studies. So studying math lets you go into a lot of different fields. I didn't even mention economics or finances. All of that is rooted in math. Okay. There's something to be said for why study math even if you're not a major. Well, having the math mindset of being able to abstract, and that's very powerful. I don't think I'll be able to convince you that in this talk, but being able to understand things mathematically, logically, it's quite important. Okay. I want to share one more blurb about teacher. People make a joke that mathematicians can only become teachers. And I want to motivate, like I'm a teacher, I'm a math teacher. Some of my colleagues here are also math teachers. Every school needs two departments in Canada. They need a math department and an English department. Like I know in high school, there's also science teachers and PE teachers, but when you get to post-secondary, not every school has every department, but math and English, you need it. So there's actually a huge demand for math teachers and the supply isn't necessarily so high. So we joke that math, you can only be a teacher. That's not entirely true, but there's a huge demand for math teachers. Okay. Finally, I want to highlight my mentor from ExxonMobil. ExxonMobil is an oil company. Think Shell. Okay, so this guy. I worked with him in a workshop for 2 weeks, and I thought his career was a pretty selling, like what I'm trying to tell you, that it keeps you flexible. Bob worked in a squad of people that would go to oil sites and determine whether or not they should mine this oil. So it's a really expensive industry. He worked in teams of like 2 engineers, a geoscientist, a computer scientist, a physicist, and him, the mathematician. He explained that his role on the team was to like translate between other people, because sometimes the computer scientist and the physicist don't necessarily speak in the same terms, but the mathematician can figure out what both of them mean and liaise between them. So he's a bit of a jack of all trades. He does do a little bit like, okay, he's not the specialist in anything, but he's very flexible. So I'd say that's the key thing to math, that it keeps you very, very flexible. You can also go be a math researcher, whatever that means, but math tends to overlap in a lot of different sciences. That's my answer.
Excellent. And since you already have the screen, why don't we turn to your presentation now on and answer the question, why does the dark side of the moon have more craters than the Earth's side?
Thank you. So this is a question that I thought was pretty neat that highlights math modeling. So I have to explain my terminology a little bit first. The dark side of the moon is the side of the moon we don't see. So a little bit of physics. There's something called tidal locking where we always see the same side of the moon. That's this side. Okay. So Earth and moon are both spinning in a way where we always see the same side. You might have heard this called the man on the moon. Okay. So we always see the same side of the moon on Earth. Now, observe that from the other side, there are a lot more craters than the side we see. Okay, a crater is these holes. I want to call them holes. I don't know. It's when an asteroid or something. I don't know if they're called asteroids. When outer space rock hits the moon, it leaves a crater. Okay. Now, question: why does the far side of the moon, the side we don't see, have more craters than the side that we do see? And I'd love to hear answers to this. I really believe in active learning, so I'll turn it to the chat. I'll give it a couple, like 30 seconds or so. Why does the far side of the moon have more craters than the near side? And I'm going to monitor the chat. I want to see if anyone could. Any ideas? Does anyone? Why is there more craters on? Okay, so at this point, usually, okay, let's see. Someone posted in the chat. Do we have an answer? You can hide from the cameras. But okay, but the far side doesn't have anywhere to hide, right? The near side can hide behind Earth. So I will just give the answer that a lot of people often say, usually when I run this. Someone would say that the Earth acts as a shield. So craters come from a comet coming and hitting the moon. So on the side, there's Earth. Earth would act as a shield. Does that make sense? And so there's some comets that would hit the moon, but instead it hits the Earth. And so that's why there's fewer craters. Does that make sense? Okay, well, this is a hypothesis because it's just a guess, right? We don't know if that's true or not. In science, well, hypotheses are obviously not necessarily true. In order to demonstrate something is true, how do you do that? You can't just say like, oh, I'm the best person there is and call it a day, right? You need to prove that. How are you going to prove that Earth acts as a shield to the moon? Are we going to launch a bunch of nuclear weapons at the moon and see if Earth acts as a shield? Well, that's not really a feasible way, okay? So we're kind of at a dilemma. We have this hypothesis. We think that Earth acts as a shield, but we can't test it because you can't launch a bunch of rockets at the moon. I mean, maybe you can, but that's dangerous, right? So the way that you do this test is you run a computer simulation. Okay, you define, it's actually almost like whatever this gave this dot. You define a dot in the sky, you call it the Earth. You define another dot, you call it the moon. You can describe how asteroids move by encoding a bunch of physics and like solving a bunch of equations. And you run the simulation. And if you run the simulation, you would find that Earth actually does not act as a shield. Okay, so it's proven you run a computer simulation where you simulate the Earth, the moon, and a bunch of asteroids. And then you'll see that Earth does not block it. Like a lot of the asteroids that would hit the moon would not hit the Earth. Some of the intuition is that the Earth blocks out less than 1% of the moon's night sky. And moreover, Earth actually, the gravity will cause some asteroids to hit the moon. Okay, so I will answer the question. The fewer craters are because of lunar volcanic activity. It has nothing to do with, maybe it has to do with Earth's gravity pulling the volcano. I don't know. Okay, I don't know about that part. But it is not Earth acting as a shield. So the takeaway I have here is math modeling is a really powerful way to simulate. Okay, when there's things that we want to know, but we can't observe because observing or simulation could bias the results, or because you can't actually test it, people will create these theoretical things mathematically, and they'll run the simulations on the math. And this is actually what I do. Math modeling is what got me into mathematics. My definition is using math to solve anything. For example, I simulate healthcare systems. Should we roll out more vaccines or should we do more blood tests? Which one's cost effective? And I would run a mathematical, I would model the healthcare system. I would simulate what happens if you do blood tests. I would simulate what happens if you run vaccines and see which one is better under the math scenarios. And this is how I use math in healthcare or to simulate the moon, I guess. Okay, that's my talk. I hope you enjoyed it.
Nice. It's math allows us to see the unseeable or the untestable practically. So Zach and Daniel, this next question's for you. What struggles did you face while becoming a mathematician or as a mathematician? And what would you say to somebody who doesn't like math or struggles with it?
Daniel, do you want to go first?
Sure, I could go first. Okay. Well, I mean, I would say, one of the struggles I had as a mathematician, sort of, I guess I have sort of two different blocks of answers here that are a little different. But indeed, as I was mentioning before, I started on the research track, and I put myself in a position where my daily life, my ability to get my paycheck, pay my bills, da 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 da, was dependent on doing mathematical research only. And eventually I figured out that, maybe that wasn't the only thing I wanted to do. Maybe I didn't want to be sort of completely solely focused on that. And that's even, even though I love math, even though I love doing research, that wasn't necessarily sort of the only thing that I wanted to do. It's also, I don't want to dissuade anyone from going into academia. It's very exciting, but just sort of the academic process, the PhD, the postdocs afterwards, it does take a while if you want to take the academic route to sort of get a job like that. If you add up undergrad, PhD, and two postdocs, that was sort of 16 years of pseudo schooling. So that's a while of a fair amount of training to get into something. But ultimately, I mean, one reason I share this is because I was sort of able to write myself, all the while though I was doing something and I loved it, but I didn't love every single aspect of it. Like I was able, and I think many people in many sort of areas of mathematics, or similarly to what Jeremy was saying, is that it is possible to sort of pivot to something if you have a mathematical background. If you love math, you can find something somewhere, and I was able to successfully pivot to teaching. But the question about students struggling, I understand that my experience that I just talked about might be very different for students. But another thing that's been mentioned before is mathematics is very collaborative, at least at the research level. We love talking to each other about problems. We love working on things together. And something I urge, all of my university students when I'm teaching them is to try to talk about mathematics. If you're struggling with it, don't just sit at home at your desk, on your couch. Don't just bang your head against something solely. Think about, what's going on, talk about it, try to suss out the ideas. If you think this is a stupid topic and you don't like it, tell your teacher that and say, why are we learning this? What does this have to do with anything? Because there are connections. That question does have a good answer, often lots of good answers. And no one should feel bad for sort of thinking that. Like if you see something mathematical that's very abstract and it sort of looks like it's something that doesn't have any use to the real world, I promise you it probably does. And you're going to do yourself a favor if you speak up and say, hey, could I learn a little bit more about this? Because right now this looks like gibberish to me and I'd like to understand it a little better. So that's what I'd recommend.
Awesome. And we'll turn to Zach.
Thanks. One of the first problems that I had becoming a mathematician was knowing that you could become a mathematician. So similar to what Karen has said and Daniel about in grade school, I didn't care that much about math. It was kind of boring. But I learned in university that math is a lot more like puzzle solving and trying to figure out what's happening with some strange situations. And then I liked it. Um, and then my second big problem that I had was more also similar to what people have said, like what Sophie and Karen said about working with other people. I started doing a PhD in number theory at a place where there was only one number theorist who was working there. So I could really only talk to him. And sometimes he had some students, some of them graduated before me, and I didn't really have a community of people that I could talk to about math problems. So when I got stuck on problems, it was really frustrating. We ended up, I guess Jeremy was asking, what do you do? What do you do with a PhD student who is maybe stuck on a problem and doesn't have a problem? This is before the meeting started. And I have a bad answer, which is change their problem a lot of times because I ended up dropping out of that program when I couldn't solve the problems and just jumped around to different things. Then I spent a couple years doing consulting. So similar to what Jeremy has said about this person who works with other groups of engineers, I worked at an engineering firm helping the chemical engineers and the computer sort of simulation engineers and the people who are building the machines to do water purification systems, helping them all understand what each other knew and could prove and was definitively safe for water purification because they don't all say the same things or have the same sort of standards of proof. And as a mathematician, I can come and say, oh, I can definitely prove that this is true. And here's how I'll convince these other groups about this. Or I can find a counterexample to this thing. I know where you need to look and how your simulation might be changed to make it more accurate. Um, After that, I decided I didn't really like working on other people's problems and I wanted to work on problems that I picked. So I re-enrolled in a different PhD program that had a big number theory department and then finished my degree pretty quickly after that because I was already prepared to do a lot of problem solving. So I would say some big issues. If you know that it's a thing that you like doing, solving puzzles and stuff, know that there's like a whole field of people and a community of people who also love doing that. Uh, and if you are struggling with some things, try to reach out to them and talk to other people who are also struggling because we can help with this. I think I get to talk now, right?
I was going to say, why don't you tell us, so thank you very much for that answer. Why don't you tell us a little bit about finding new numbers?
Sure. So what I do right now, and let me move this over a little, is looking for different numbers that are kind of like our usual counting integers and negative numbers. So our usual integers are like all the negative, -2, -1, 0, all the way down, and then 1, 2, 3, 4, all the way up. Um, and we like them a lot, and they have certain properties that we like. We can talk about primes, we can multiply them, we can add them together. So we want to find more numbers kind of like that. This is one that I pulled straight out of a talk that I'm going to give in a couple weeks. And I want to pick a number, and I'm going to call it B. It's a different number. It's not any of the integers. It's not a usual real number in any sense. And I just say it has this property. If I multiply it by itself 6 times, B times B times B times B times B times B, B to the 6, I should get the same thing as if I multiply it by itself 3 times minus 5. If you ask a calculator, what is this number? It will say, this is not a number. If you ask a very sophisticated calculator like a Wolfram Alpha, it will say, actually, there are 6 complex numbers that do this, but I don't really care about having a formula for it. And a fun thing that we get to do in math is sort of define something by its properties instead of knowing exactly how to write it down. Maybe an analogy is like, if you have a dog at home, like Jeremy, then I could say, it's the dog at Jeremy's place. I don't have to know the dog's name. I know that there's a defining property that is this dog. Maybe there's 2 dogs. Okay, I have to be a little more careful. But a lot of times what we do is we say, just think about what the property is, and that tells you what the thing is. So if I use these numbers, I can generate a whole other world of numbers. And in this new world, we have all the regular integers, but we also have things like b. We have things like b times b. We have things like 5 times b. We have things like b to the 4 plus 1. We have a lot of different combinations of these. And these we call a ring of integers, which has an interesting historical meaning and definition. The fact is, nobody knows why it's called a ring or what the meaning of ring is. David Hilbert named it 130 years ago in a different language. It comes from German, and he never wrote down why he called it ring. So it's been translated, and some people will say it's a ring because it loops around. Because if you do b times itself, after you do it 6 times, you get back to b to the 3 minus 5. So you have this whole big long line of integers, regular, -1, -2, all of those. And then you have some b's, and you can combine them. But if you get all the way up to b to the 6, you loop back around. Now, our problem is we don't necessarily know if these are all of the different things in the ring of integers. So this is kind of like saying, I want to know about all of the dogs in Canada. I definitely don't know all their names. I can say, let's just consider that a big collection, all the dogs in Canada. My task is then, how do we decide if we got them all? How do we write them all down? And there's sort of a silly way to do it, which is kind of equivalent to go and knock on everybody's door and see if they have a dog. And if they do, write down its name. And that's one way that solves this problem, but it's not a very efficient way. So my work is in trying to find more efficient ways to decide, did we get them all? How do we write them down so that people can do computations with them? These are now very popular for things in quantum cryptography, where people need to have interesting rings of integers so that they can hide secrets in a world where quantum computers exist. That's all I want to say about these things.
I'm conscientious of the time, so I want to make sure that Daniel, that you have a chance to present yours, and then I have one quick question for Sophie, and then we'll look at wrapping up. So Daniel, I'll turn it over to you and error correcting code.
Okay, so I want to talk a little bit about something called error correcting codes. And like Zach, I also study number theory, and there are some, definitely a lot of computational aspects of it. And I'm going to sort of tell you about one of them. And so basically, just to give a quick what I'm doing, because there's going to be a couple technical details, I just want to tell you about, we've been talking all about puzzles and solving them and how fun it is. This is sort of a quick puzzle that when it was solved, it really, allowed us to make computers work. So a fun little problem, but a very interesting one and a very important one. So when you're dealing with computers, anytime you want to transmit information between computers or store information in a computer, essentially, at least contemporarily, it's all stored as strings of ones and zeros. But this can be a problem because we like our ones and zeros. Our ones and zeros give us the particular files, the particular data, the particular information we want. But what if we say store this on a disk, like a video game or something, and then that disk gets scratched and some of the information is damaged or lost? Similarly, what if we are beaming either a Wi-Fi signal around a house or a building, or maybe beaming messages through space? Well, interference and static can mess these signals up. And indeed, another thing, the way that this can happen is within a computer processor. What can essentially happen, or what mathematically we can model as happening, is if you have a string of zeros and ones, what could happen is some external factor could switch some of these ones and zeros around. Maybe you really want 10101, and maybe something changes that message either in memory or through transition to 10111, which is bad. Because if your ones and zeros are important, you want them to be left alone, but this is simply something that we can't depend on. So the question is, well, how do we deal with this? How do we deal with the fact that to make computers work, to make, our data transmission feasible and safe, we have to make sure that these strings of ones and zeros stay uncorrupted, but this is just something that happens very naturally, as we've seen in a couple of examples. And I'm going to give you a very basic scheme of how to at least help prevent this. And how this is done is using something called error correcting codes. We can potentially, if we store or transmit our data in a specific way, instead of it getting all staticky or jumbled up or damaged, even if some damage occurs, we can still get full fidelity. So what's one way to do this that's very simple, but I still think very powerful? Well, it's called replication. Imagine if instead of sending individual ones or zeros, we send blocks of these. So for example, what I have drawn here is instead of sending just a 1 or just a 0, we send, for example, 27 ones or 27 zeros. So to transmit the message 101, we'd send 27 ones, then 27 zeros, then 27 ones again. And why would this help? Why would this work? Well, I will tell you. Let's draw a picture of this. Let's first, so that we can draw a picture, let's imagine ones are black dots and zeros are white dots. So instead of thinking of ones and zeros, let's just think of these as black dots and white dots. And that's what we're sending over channels. That's what we're saving on our disks, on our hard drives, etc. But what would replication look like? Replication would mean if we want to send a 1, we don't just pick an individual black dot. This is a big square, a whole bunch of pixels here. A 1 we represent by a whole bunch of black dots, given the pixels on this screen, there are hundreds, maybe thousands of black dots here. And if we wanted to send a 0, there are probably thousands of white dots here. So imagine either we store this on a CD and it gets scratched, we try to send this message and it gets a little staticky. What would this look like if we sent these and some of the bits flipped, say, during transmission? Well, I posit it would look something like this. The black dot, if some of the bits flipped, it would start looking like this. It would sort of look like a staticky TV, and similarly for the white dot. But so long as few enough bits ended up flipping, I argue that the black dot would still look mostly black, and the white dot would still look mostly white. And therefore, even though the signal degraded, and even though there was potentially some damage to the signal, we could still fairly easily, in fact, tell what the message was supposed to be, so long as we add some redundancy into the message. And you can sit down. You don't have to just go with the picture. You can sit down and you can calculate some things like on the back of a napkin. If, for example, you're in a situation where each bit that you send, each 0 and 1, has a 10% chance of flipping, well, then just with that, every 1 and 0 you send has a 90% chance of being received correctly. If you triple the bits, that ups the success rate to 97.2. It goes up over 99% once you pass 7. And if you do, say, 27, like I said before, a very high chance. 81 is one that I calculated quite high as well, and so on and so forth. You can actually get this as good as you want, and you can essentially solve this issue of, I don't know if you heard that thunder outside, but it was very loud. You can essentially solve this issue of static with these error correcting codes. And in fact, I can't get into the details, but this is actually how we're having this conversation right now. All the way back to the start of computing with computers and punch cards to modern computer processors, these error correcting codes are actually built right into the computers themselves to help make sure that everything works. And even if heat or cosmic rays or something comes in and bombards our computers and changes some of these ones and zeros, so long as it changes few enough, everything still goes through correctly, and we can still, for example, have a conversation at a distance. And indeed, this is the main point I want to say. It's a fairly simple problem. You're thinking about sending ones and zeros. There's a chance of error. How do you fix this problem? How do you at least make it more likely that a signal is sent with fidelity? And this at least gives one solution to this. And the secret, which I don't have time to talk about, is these codes that I've given you, they work, but you can actually do quite a bit better than this. This is a good idea, but it's not quite good enough for practice. The code I gave you isn't actually what's used in modern computers. But as you learn more mathematics, as you continue to learn and develop and grow and go down the rabbit hole, you can learn these how to do this problem better and better. And for example, error correcting codes have facilitated space travel and being able to take a glimpse of the cosmos, because the only reason we can get images of the solar system via space probes is by developing these error correcting codes to make sure that we can send these signals through the solar system without them degrading too heavily. And that's really all I have to say.
I have a question for Sophie specifically that I quite like. What type of student, in your experience, would you say are good at math, and why?
I feel like people might be able to guess this based on what we've heard today. But in general, I don't think there's any particular kind of student who is good at math. I think maybe what you've heard from all of us is that it helps to be curious about things. And I think that's it. So if you heard anything today that made you curious to learn more, then you should become a mathematician, possibly at the University of Waterloo.
Excellent. Well, thank you to all of our presenters so much. As I mentioned, there will be a recording of this. If you want to learn more about any of this, please check out fieldsacademy.ca/AAM. You can also email me, pbertai@fieldsinstitute.ca. And if you have a chance to stick around, we do have a couple of other questions and whatnot. We're also happy to answer anything that you'd like to ask us. The one thing that I did want to mention is a question that I often get asked is, and it's been brought up a little bit as well, of when am I ever going to use this? Where do you see math in the real world? Why should I be learning this math? And my answer to this is always the same. Math is in everything. It's all through the world around us. It's foundational to everything we do. I've never found a subject that, or an area where math isn't found. Some people call it a language in that it uses its own symbols, like numbers and letters and special characters, like our plus, minus, equals, that helps us explain the world around us. It's also an art. Some of you have mentioned today, math for math's sake, just doing it because it is this beautiful subject. And it has applications we wouldn't have thought of before. So it's also a science, and we can use it to solve puzzles, which you've heard mentioned quite often, in problems, and we can apply it to the world around us. So I haven't found a subject or an area that math isn't involved. And my challenge to all of you is to look around and see if you can find it everywhere as well. So a big thank you to our panelists for today. And thank you all for joining us. And I hope you have a wonderful summer. Wonderful. So I don't think we have any direct questions from the audience at the moment, but I know that we did skip over a question about technology. So Karen, did you want to take this, and then I'll open it up if anybody else has an answer for it as well. Basically, in math and physics, you use some unique technologies. If you want to tell us a little bit about that.
Sure. Yeah. So personally, mostly what I use is just computers, and other people obviously do too. We've heard some other computational work. For my own use of computers, a lot of it is to explore possibilities. So I'm interested in some kind of property of some sort of discrete object, to answer some physics question, and I want to try to work it out systematically on large numbers of examples, to see if to build an intuition and build conjectures that I can then hopefully prove. I have done some rigorous computational work where you actually prove stuff with your computations. In the most extreme case, for me personally, that involved a 6 million by 6 million matrix that I needed to iterate. Anyway, now it's funny though, because I do work with high energy physicists and they have the really cool tech, or some really cool tech. And in fact, I mentioned my 6 million by 6 million matrix to one of my high energy physics colleagues, and he said, "Oh, so you didn't really try." That isn't even big from his point of view. Because they're the people that work with, say, particle accelerators and other super cool stuff like that. And the amount of data that a particle accelerator collects is just remarkable, to the point that you can't even hope to actually just collect the data and then analyze it. So one of the big things in that world, in fact, is appropriate triggers to know when this is a moment when you're going to actually save the data, because you just can't save it most of the time. And then the accelerators are themselves pretty cool. You've got these giant rings in Switzerland under the mountains with these beams of particles at incredibly high energies colliding into each other.
Very nice. Anybody else kind of want to, I know Jeremy, you had mentioned about using, coding and, computer simulations and that type of thing to explore your work. Yeah, did you want to expand on that, or anybody else want to jump in?
Thank you. I'd love to expand on that. I'll be very brief. I think Karen explained it really well. It's used for simulation. So this is similar to my moon talk for my master's thesis. One thing that was a tangential problem was trying to study how honeybees stay warm. So if you want to measure how, like, if a hiveless honeybee cluster can be exposed to freezing temperatures, but they won't freeze to death. So we wonder how, like, how can bees have no shelter, be lower than 0 degrees Celsius, and live? So the problem with measuring it is that if you want to measure it, you need to put like a ruler or a thermometer in there. That itself will bias your results, because doing that will make the bees move. So when you can't run these experiments, that's when people will encode it in a computer and brute force solve and simulate to see what's going on. And a lot of these like computer simulations are the best type of evidence you get. So computers allow you to brute force simulate. And then based on those simulations, you can believe or not believe your hypotheses.
Excellent. Anybody else have, and pen and paper, by the way, is a perfectly valid answer as well.
I have a quick thing to add, just sort of pragmatically. Like I've definitely had, sort of undergrad students work on some math problems with me. Like sometimes there's something that maybe I could solve on my own, maybe I couldn't, but it would be fruitful for all involved to get a bunch of students who are interested in math to work on it. And there's definitely times where there's maybe some algebraic problem that maybe you could do it by hand if you understood it to start. And this is very similar to what other people said, but like in, pragmatically, I've definitely sent away, groups of undergrads who have known how to code, and I've said, I want to know how this algebraic thing works. Try to code it up in a computer, try to see if you can do this. And even, you can even sort of get ideas, as everyone else said, for proof-based mathematics, but even not just within the research sphere. Like I've definitely been able to work, at least with students at the undergraduate or even sometimes at the high school level. And so if you're a high school student and know how to code, you could potentially collaborate with a mathematician, and that could be a great foray into mathematics.
All right, so I'm going to throw out one kind of last, just open question for all of our panelists. You can kind of, we'll go through the order we did at the beginning. Any final words or anything that you'd like to kind of put on the record about being a mathematician or mathematics in general, or just anything that kind of came up that you just wanted to make a comment on. So we'll start with Sophie.
Well, that's a lot of pressure. Um, I hope that everyone had fun today and that we've convinced you that there's a lot more math to learn out there, and maybe this will motivate you to learn some of it or all of it, but I think that would be quite hard.
Excellent. And Karen.
Maybe so something that's come up implicitly, a lot of us have talked about how collaborative mathematics is, and I know that's something that I didn't realize when I was younger. I have a friend from junior high who's actually a prof in classics, and her day-to-day work is much more solitary than mine. A lot of reading and thinking and writing. And I mean, okay, I read and think and write too, but I do a lot of talking with other people. And I don't know. I mean, the students here in the audience can tell me what you guys think, but I think most people wouldn't expect that. But it's actually quite true. It's quite true across STEM fields, but math is a very good example of it. And I think the last thing I would say is, this has also been sort of implicit, but maybe I want to make explicit, is you don't necessarily have to know where you're going for it to be worth doing things along the way, and things can change. Like I started as very much the kind of pure mathematician who thought applications were dirty and I did not want to touch them, and now I do mathematical physics. So you don't have to know where you're going, and you can still get.
Oh, I think she froze at the they froze at the very end there. Jeremy.
Thanks. Yeah, so I think math is really powerful in the sense that why abstraction is so powerful, because when you abstract enough, you shave away the fluff and you can see the problem for the truth, what it is. Poincaré said that mathematics is the art of giving different problems the same name. So one of the examples I can give you here is it turns out the dynamics of a disease spread like COVID-19, it often we model it with exponential equations. You solve it and you get exponential equations, which is the same as interest in your bank. So math allows you to say, because I understand how compound interest builds in my bank, I can apply it to a pandemic and understand the disease dynamics, which is actually a really powerful thing. So math with abstraction, it lets you take things you solved in one area and apply it to another area. And other places do this too, but I think math is really with abstraction and shaving away the fluff and for taking problems as they really are. Math gives you this tools and the problem-solving methodology to problem solve, take things you've learned before and apply it in other contexts.
Daniel?
Yeah, one thing I'll say, I think though I echo, I mean, I echo what a lot of other people have said, so I'll say a different thing. What I'll say is you don't have to push yourself way out of your comfort zone. You don't have to take all the math in the world all the time, constantly. Maybe you want to, maybe thinking about it will convince you that that's what you want to do, and if so, great. But technology is growing. There's all sorts of things that are becoming more technical. It is nice to take a lot of math. It does help. One specific example I'll use is a lot of my friends in undergrad actually went on to economics PhDs, and in some cases beyond, and they were all math majors starting out. And in fact, a lot of, at the very least at the time, circa a decade and a half ago, economics departments were saying it's probably easier to teach a grad student economics than it is math. Let's just get math people in for our PhDs because mathematics is so important. There's also something people say that roughly every 10 years, what was mathematical economics 10 years ago is just regular economics now. So just no matter what sort of career you want to go into, knowing more mathematics is becoming sort of day by day by day, the technical side of things becomes more important, and habituating yourself, learning a little bit more about, why math might be interesting, might simply be in your best interest. And that's something that I would recommend.
And Zach, any final words?
Sure. So I really like that math is a good training ground to figure out how to solve problems and then also how to communicate those solutions and your questions to other people. And those are really valuable skills no matter what you're going to be doing. Those are things everybody is looking for. We want to have problem solvers. We want to have good communication skills. And math gives you an environment where you can do that. You can figure out if your solution worked or not. It's at times very frustrating, but now I find when I'm in a new situation and I have to solve a new problem, I don't get frustrated like other people might. I go like, okay, well, what do I need to know? What do I think is happening here? Can I like get rid of the fluff? What's important? And then just critically analyze my thought process and figure out what I should be doing. And then when I do figure that out, I can then explain it to other people in a way that they understand because I'm asking them questions and they're asking me questions. Uh, and we are figuring out what's going on. And I want to, there's a little response here of like maybe people in the future who have used ChatGPT a lot will not be very good at communication and will not be very good at problem solving because they haven't practiced these things. But if you are studying math and you are working on these skills, it's going to be frustrating at the time. It's going to feel like you're messing up a lot. And that's true because you're learning how to do the stuff. But then you will know how to do the stuff. And other people will not know how to do the stuff.
Excellent. Well, thank you all so much for joining us today. Thank you to the panelists. Thank you to our listeners. And we hope that we were able to inspire a little bit today and provide a little bit of insight into what it's like to be a mathematician and what that kind of journey is. So thank you so much. Really appreciate it.